Hey guys, today we're going to take a look at a little bit more stoichiometry, limiting reagents, which you guys should be good at, gases, which is pretty much brand new, but I've been intimating that this would be coming sooner or later, and also we'll be looking at percent yield, which we've done before earlier in the year a few times. So the first thing is a little refresher. 1 mole of any gas takes up how much? And the answer is 1 mole box. 1 mole of any gas takes up this much space. It's weird. It doesn't matter what kind of gas it is. Oxygen gas, O2, weighs 32 grams, but it's still, if you release it into this box, it would take up this much space. A little teeny tiny atom like helium only weighs 4 grams per mole, 6.02 times 10 to the 23rd particles of them, weighs 4 grams, but it would still fill up this much space. So if it's a big molecule, if it's a little molecule, it's kind of interesting that gases only take up this much space at standard temperature and pressure, so 22.4 liters at 0 degrees Celsius and 1 atmosphere of pressure, about, like at sea level, how much pressure is being put on us. All right, let's do a sample problem. 3 grams of copper are placed in a reaction vessel of some sort with 0.0220 liters of fluorine gas. How many grams of copper 2 fluoride will be made? All right, our reaction is copper solid, so it looks like a penny. It's just Cu with no charge. You can put a 0 there if you want to. It's a solid. We'll take some fluorine gas. Fluorine gas is one of the lucky 7. So that means they find buddies and they form pairs, partnerships, and that's a gas. It's a diatomic fluorine gas. And then it makes copper 2 fluoride, all right? The Roman numeral 2 means it's one of the D block elements. So copper with a +2, and fluoride is fluorine after it gains an electron, gets a -1 charge, +2 -1. So you need 2 fluorides to go with 1 copper 2. We need to balance this reaction always. Remember, you have to balance it, all right? So we got the skeleton reaction done. Let's balance 1 copper, 2 fluorines, 2 fluorines. Yeah, it's good. It's a 1 to 1 to 1 mole to mole to mole ratio. All right, what's the question asking? How many grams of copper 2 fluoride will be made? So I'm looking for this. That's my final answer right there. How many grams? 0.0220 liters. All right. So we have to get over here. It looks to me like we are not going to have to do anything with this entire column. There's nothing in the question. You can do it if you want to. But what we're going to have to do is go from liters to moles somehow or other. Once we get the moles here, then we can figure out the moles of the copper 2 fluoride. And once we have the moles, we can calculate the grams of this. So we could either take this and go 0.0220 liters is how many moles? Our mole box says that it's 22.4 liters per mole. So where am I going to put liters and moles? Liters goes here, moles goes here. 22.4 liters per 1 mole. I believe that liters will cancel with liters. And so my math is going to be 0.0220 times 1, hit enter, divided by 22.4, hit enter, and we have 0.1230 zeros and a 98. We need one more sig fig here, 982, and that's moles. 0.000982 moles. Well, the next thing we want to do is figure out the grams of copper 2 fluoride, so we need to get the moles of copper 2 fluoride. This is still moles in this row across here. It's a 1 to 1 ratio. 1 is to 1 is 0.000982 is 2.000982. And now we get the grams in the normal manner. In other words, we'll use our moles equals grams over molar mass calculation.
Molar mass of copper 2 fluoride, copper is 63 and fluorine is 19, so 63 is 101. I think it's 101 grams per mole. You should check me on that, but that's how it works anyway.
Let's see, and grams equals moles times molar mass. So I'll take molar mass times 101 times 100 times bigger than that, 0.0992 grams of copper 2 fluoride would be expected to be made. Simple, right? Let's take a look at the next problem. We want to make 72.052 grams of H2O by using a synthesis reaction. So a synthesis reaction means we're going to synthesize, we're going to make H2O. What are we going to make it from? Oxygen and hydrogen. Oxygen is one of the diatomics, so is hydrogen. We need to balance this. 2, I need 2 there, I need a 2 there. I believe it's a 1 to 2 to 2 mole to mole ratio. So I can have my usual grams per mole, which is molar mass, and moles. And I'll also need liters for at least one of these two. And you only use liters for gases. Gases only. You want to make that many grams, 72.052, 5 sig figs grams. So here's the row across with grams, 72.052 grams of water. By using how many liters of H2 will you need? So the only question that's being asked is this one right here. How many liters, here's the liters, how many liters of H2 will we use, okay? So what we need to do is somehow or other get our moles of water using 72.052 grams, get the moles, and then it's a 2 to 2 ratio, 2 is to 2, you know, it's the same number. And so we'll get the moles of this, and then we'll simply use our mole box, 22.4 liters per mole, to calculate this. So I don't think we're going to need this column at all. I don't think we're going to have to do anything with those two. Water is usually a liquid, so you would never do liters for a liquid in this case. The liters works for gases only. Now, this might be a hot reaction, actually. So it is conceivable that you could be asked, well, if this is water in a gaseous form, then how many liters? But I'm not asking that. We can use our usual calculators, moles, grams, molar mass. And there's another one that you can use too. It's moles times 22.4 liters per mole. And that equals our liters. Once again, our steps are going to be go from grams to moles somehow or other, then moles across to moles here, and then calculate the liters down below. So water's molar mass, you've seen that quite a lot. It's 18 grams per mole. So if we want to get the moles, grams divided by molar mass,
72.052 divided by 18.000,
and that gives us 4.0034 moles. So I'm using 5 sig figs. And it's a 2 to 2 ratio. 2 is to 2, as 4 is to 4, 4.000. All right, so now we want to get the liters of H2. To get liters, cover up liters, moles times 22.4, take 4, so it's 4 moles. So it's 4 times as big as the mole box. So 4 times 22.4, which is 88, isn't it? 89 point something, something, something. You can go ahead and calculate that. Okay, so the other thing that we wanted to do today was, along with talking about liters of gases, we want to talk about percent yield and percent error. We've done these before in labs. And percent yield means how much did you get compared to what you're supposed to get. I was supposed to get 85, but I only got 80, so my percent yield is 80 divided by 85 times 100. My percent error is how much did I miss by, divided by what I was supposed to get. And so in this, you have access to this PowerPoint or this slideshow, and it has the formulas here for you, but you can really do this just using your common sense. So in this example, you start off with 2 grams of HCl and 2.035 grams of calcium hydroxide. So this is a limiting reagent problem. All right. So I randomly put in 2 grams of HCl here and 2.035 grams of calcium hydroxide here. Using molar mass, we calculated the moles. All right. So what do we have to figure out which is the limiting reagent. So we cover up the moles. Let's see, it's right here, moles of hydrochloric acid, and here's the moles of this. So it's balanced already. It's a 2 to 1 to 2 to 1 mole ratio. So I say 2 is to 1, as 0.055 is to, what's half of 0.055? It's 0.026 to 0.027. 0.027, oh my goodness, it's exactly the same. Okay, so neither one is the limiting reagent. So they both run out at the same time. I put That's what we're worried about. We really want to know about calcium chloride, all right? So we're not going to talk about water in this case. So we'd say, all right, it's a 1-to-1 mole-to-mole ratio. So I'll use this one. 1:1 as 0.0275 moles is to 0.0275 moles. So then I can calculate my grams. All right, so calculating grams equals moles times molar mass, multiply those two together and you get 3.05. That's how much we should end up with in this reaction. Now, every time you do a reaction, you kind of mess up a little bit. You lose a little bit, it gets stuck to the glassware. Maybe you spill a little bit, maybe some of it somehow or other evaporates. This probably wouldn't evaporate, but sometimes things will. So I'm supposed to get 3.05, but I actually got 2.5. So my percent yield is going to be 2.5 divided by 3.05 times 100. And my percent error is how much I missed by. I was supposed to get 3.05, and I actually got 2.5, so I missed by 0.55 out of what I was supposed to get, which is 3.05. And so that would be my percent error, how much I missed by. So it's common sense. And so that's a general idea about gases and a little refresher on percent error.